Today's topic is binary tree traversal. In computer science, tree traversal refers to the process of visiting each node in a tree data structure exactly once and in a systematic way. Here, by visiting each node, we mean either examining the value of the node or updating the value of each node. This is the outline of the lecture. I will first review the basics of binary trees. Then I will move on to talk about two kinds of traversal strategies, namely depth-first traversal and breadth-first traversal. Breadth-first traversal is also known as level-order traversal, where we visit every node on a level before going to a lower level. In depth-first traversal, I will introduce three main traversal strategies, namely pre-order traversal, in-order traversal, and post-order traversal. Implementation details using C++ will be shown along the way. Recall that a binary tree is a collection of nodes, such that there are two types of nodes, internal nodes and external nodes. For some reason, we also term external nodes as leaf nodes. An internal node contains exactly two links, left and right, where one of them must not be a null pointer. The two links are themselves disjoint binary trees if they are not null pointer. If both the two links are null pointer, then the node is actually an external node or a leaf node. For example, in this binary tree, node A, B, C, D, G, F are internal nodes, where node A, B, C, and F have two non-empty links, and node D has only non-empty right link and node G has only non-empty left link. Node E, I, J, K, and H are all external nodes or leaf nodes, where both links are null pointers. We can also extend the representation of binary tree by drawing the empty links as squares, as shown in this slide. To implement a binary tree, we need to first define a node structure, where each node structure has a value and two pointers to its left subtree and the right subtree. Let's define a struct node where it contains data, which is the value of the node, and a pointer to its left subtree, another pointer to its right subtree. To facilitate the construction of a binary tree, we can write a helper function, makeNode, which returns a pointer to the new node. And it takes in three parameters: a value, a pointer to its left subtree, and another pointer to its right subtree. To make it easier for the user, we can give default value to both pointers as null pointer. This function will simply return a new node with all these values set according to the values given in the parameters. With this helper function, we can create a simple tree as follows. We first create a node with value equals to 20, and it has a left subtree, which is actually a leaf node with value equals to 10, and a right subtree, which is also a leaf node with value equals to 30. And then we create another node with value equal to 70. It also has a left subtree, which is a leaf node with value equals to 60. And a right subtree, which is also a leaf node with value equals to 80. And then we can create the root node with value equals to 50. And its left subtree is the tree rooted at the node with value equals to 20, and its right subtree is the tree with the node value equals to 70. This is how the simple tree looks like. Here we don't draw the empty links. We can traverse binary trees according to different strategies. Under depth-first traversal, we can traverse the tree using pre-order traversal, in-order traversal, or post-order traversal. Pre-order traversal first visits the node, then traverses the left subtree, and finally traverses the right subtree. In-order traversal first traverses the left subtree, then visits the node, and finally traverses the right subtree. Post-order traversal first traverses the left subtree, then traverses the right subtree, and finally visits the node. Let's look at an example. I will only give step-by-step example for pre-order traversal. People watching this video are encouraged to go through the other two traversal strategies by themselves. Suppose we want to traverse this tree using pre-order traversal. According to the strategy, we will first visit node G, which is the root node. Then we recursively traverse the left subtree rooted at D, followed by the right subtree rooted at K. Now we have the root node G at its final position in the visiting sequence. Next, we'll recursively traverse the subtree rooted at node D, following the same pre-order traversal strategy. That is, we first visit the node D, then we visit the left subtree rooted at B, and finally visit the right subtree rooted at node E. Now, node G and node D are at their final positions in the visiting sequence. Next, we will traverse the subtree rooted at node B. Following the same pre-order traversal strategy, we first visit the node B, which is the root node in this subtree, and then we traverse its left subtree, which is actually a leaf node A, and right subtree, the node C. We'll keep this process until we reach an empty link, which means where we meet a leaf node. So now we have 5 nodes at their final positions in the visiting sequence. The next is to traverse the subtree rooted at node E, following the same pre-order traversal strategy. And this is the pre-order traversal of the root node G and the left subtree of it. I will leave the traversal of the right subtree of node G to the audience. If you are following the same approach, you should have the pre-order traversal of the tree as shown on this slide. To implement pre-order traversal, we need to first define what does it mean by visiting a node. Here we can simply define visiting a node as printing the value of the node. Therefore, let's define a simple function called visit node. It takes in a parameter, which is a pointer to const node, since we are not changing the value of the node. And this function simply print out the value of the node. Since we are using cout, the O string, we need to include IO string. Now we can implement pre-order traversal recursively. So the function pre-order takes in a pointer to a const node. So if node is not a null pointer, we will simply visit the node and then recursively traverse its left subtree and then followed by its right subtree. We can call this function by passing root as the argument. Before doing that, let's print out some prefix message. Pre-order passing root. Let's compile the file and see the output. So the output shows the list of the nodes printed according to the pre-order traversal of the tree. Similarly, we can implement the in-order traversal and post-order traversal of the tree in a similar manner. For in-order traversal, if the node is not a null pointer, we'll first recursively traverse its left subtree. And then we'll visit the node. Afterwards, we then recursively traverse its right subtree. For post-order traversal, if the node is not a null pointer, we'll first recursively traverse its left subtree followed by its right subtree before we visit the node. We can observe the outputs of these two traversals by calling these two functions. Let's compile and run and see the outputs. So these are the traversing orders of pre-order traversal, in-order traversal, and post-order traversal. Now let's move on to talk about breadth-first traversal, which is also known as level order traversal. For level order traversal, we'll traverse all nodes on level 0 from left to right, and then all nodes on level 1 from left to right, then node on level 2 from left to right. So for example, for this same binary tree, the result of a level order traversal is this. We'll first visit level 0 node, which is node G, followed by level 1 node, which is node D and K from left to right, and then level 2 node B, E, H, M from left to right, followed by level 3 node A, C, F, J, L from left to right, and followed by the level 4 node, which is there's only one node I. To implement level order traversal, we can make use of a data structure which is queue, and the elements are first in, first out. So if node is not a null pointer, we construct an empty queue, where each element in the queue is a pointer to read-only node. And then we push the node into the queue. Next, we enter a loop. As long as the queue is not empty, we get the top of the queue, and then we visit that node. After that, we remove it from the queue. Next, we need to check if this current node has an empty left subtree or not. If it doesn't, we need to push its left subtree into the queue. Similarly, we do it for the right subtree. Now we can observe the output of level order traversal by calling that function. Let's compile the file and run it. So we have the visiting sequences for pre-order, in-order, post-order, and the level order traversals. If we refer to the tree that we built previously, we can verify the correctness of each traversal. To summarize, in this lecture, we have reviewed the basics of binary tree and covered different binary tree traversal strategies. In particular, we have covered depth-first traversal and breadth-first traversal. And in breadth-first traversal, we have covered pre-order traversal, in-order traversal, and post-order traversal. That's all for today, and see you next time.